Okay, I want to bring us back to our roadmap or our big picture for the course. And as we've talked about, we are definitely in quantitative world. We're still working through the different descriptive statistics because, as I've said before, when you're analyzing data and you're preparing either a written report or an oral presentation, you do, for your reader, for your listener, want to go through and describe your data, what's going on with the information you have collected. And so we've, like you know, gone through central tendency, measures of spread outness or variability, measures of distributional shape. Our final descriptive statistic is measures of relationship. And we actually have two, so I guess I should say statistics. We have covariance, we also have Pearson R, and regression. We're definitely going to do a lot with multiple regression next semester, but for this we'll touch on regression in a different recording. So this recording only deals with covariance and Pearson R. So let me get us to our PowerPoint. So again, measures of relationship. So far in the course, we've only been looking at one variable at a time, and so we call those univariate statistics because it's just one variable. We had one set of scores. We calculated the mean, median, mode, all our measures of variability, standard deviation, so forth, and then finally skewness and kurtosis. And so we've been describing our variables one at a time. When we get into measures of relationship, we want to look at two variables at a time. In this case, we're just looking 2 by 2 by 2, but you'll see that really measures of relationship are the foundation for a lot of statistics that we do. And so it becomes a much more complex and kind of a multivariate world, which is a good thing, right? Because in the real world, variables don't often go 2 by 2. You know, issues are not as simple as one thing related to another thing. There are often many factors that come into whatever situation you're collecting data for. So but we always want to begin at the most basic level, and then we can build from there. So for this, we're going to talk about two variables together, right? And so specifically, covariance and Pearson R, they look at how are two variables related. And you could, as you could imagine, have many examples. So just a few. How are high school GPA and college success related? What's the relationship between those two? What's the relationship between GRE and graduate school performance? Just as a piece of bonus information, I can tell you that when we analyzed it, there's not a tremendous amount of relationship for our students between GRE and how long it takes someone to graduate. So we did months to graduation, which is, I guess, a form of graduate school performance. Height at age 2.5 and height as an adult. So when my boys were very small, taking them into the doctor, it was always fascinating to me to see the growth chart and listen as the pediatrician was able to kind of predict what height the boys would be as an adult. And so now they love to tease each other about that because one is predicted to be about 6'1", the other one is predicted to be about 5'11", and my poor little baby, he's predicted to be about 5'9". So they love to torture each other with that information. And then the last example here, self-esteem and classroom motivation. So how are those two related? So you can tell from those examples, and probably a lot of other examples, that we're looking at variables two at a time. All right, the first statistic we'll talk about is covariance. And so I have the formula there for you. And I want to point out a couple of things because the numerator of this formula may look a little bit familiar to you. So I wanted to bring your mind back to when we talked about variance, let me get my pens up, sorry. When we talked about variance way back several presentations ago, but do you remember when we did sum of squares and we had x minus the mean of x squared, which is basically what? X minus the mean of x times x minus the mean of x, right? So we squared it and then we summed it. So we had the sum of x, right? And if I wrote it out instead of using the squared symbol, it's going to look a lot like what we have over here, right? And then when we divided, we divided by n, correct? The number, when we were getting sum of squares, n minus 1. Right? Okay, does that look familiar? So we had sum of squares divided by n minus 1, and I've run out of room. Yeah, it won't look, oh well, I could write it over here. That was variance, correct? Variance. Okay. Ooh, love that handwriting. All right, but the idea here, the point here is to show you that covariance is very much similar to variance. So this is talking about the spread outness of one variable, how one variable varies around the mean. This is talking about how two variables vary around the mean, okay? So instead of it being just one variable, which would have been just x, we're looking at x and y. So x and y become our two variables. So let's say that x is going to be that height at age 2.5, and y is height as an adult. Sometimes it helps to put a context on these. So if we pull the data from the pediatrician's office, where they have collected information on kids that are 2.5, and then information on how tall they grew to be as an adult of, let's say they marked it at 25 years old, because I think most boys are finished growing by then. Growing up anyway. Well, physically up, not mentally. But that's a whole nother class. All right. But you can see it's looking at how far each score is from the mean of height as a child and how far each score is from the mean of height as an adult, and they're dividing by n minus 1. Same thing we're doing over here. Okay, so far so good. So we want to look at how do these scores vary together around the mean. All right, and as an example, we have this little set of data, and we are going to work through that here in a minute. But I want to point out some things to you. If you look at height as a child here, these are x values and there are y values. If I want to see, okay, as x increases, see how it's going 1, 2, 3, 4, 5? And then y is decreasing, 8, 7, 6, 5, 4. And I can see that as one variable increases, the other variable decreases. So they have this inverse relationship. Now, I don't want to confuse you because really each row is a person. So this is a person, person 2, person 3, 4, and 5. So person 1 has a score of 1 as a child and 8 as an adult. 2 as a child, 7 as an adult. 3 as a child, 6 as an adult, and so on. So these are people. These rows are people. But if I know based on this data, let me back up and say, if I know what their height is as a child, I can perfectly predict what it's going to be as an adult. Right? Which kind of doesn't make any sense with the little practice numbers we have here, but you get the idea. X is increasing, Y is decreasing. So they have this this deal going on. You have this inverse relationship, also called a negative relationship. I think negative is kind of a weird way to say it, and that's why I use the word inverse. Now, the good thing about saying negative is the actual sign here will be negative. So when variables do have this inverse relationship, we say the covariance is going to be negative, and in this case it is, and we'll practice looking at that in just a minute. If the covariance is greater than 0, we say they have a positive relationship. And so in that case, in a positive relationship, you have the variables sort of traveling together, is what I like to say. The scores are either both going up or they are both decreasing, or they're both going down. So if I had something like maybe 5, 6, 7, 8, and 9, to where these scores are increasing and these scores are increasing, which is kind of weird to draw a down arrow with their increasing, but that's beside the point. The idea here is if instead of these values, we have these new values, since now the scores are going in the same direction, they're kind of traveling together, we say we have a positive relationship. And if covariance is around 0 or at 0, we say there's no relationship. There's really no predictable pattern whenever covariance is 0. And so if we have knowledge of X, we have very little way of predicting Y. Okay, that would be a no relationship. That would be a 0 for covariance. Okay, let me go to the next slide where I want us just to practice calculating the covariance just for this little tiny data set, just so we can sort of help wrap our heads around it. So the first thing, if I look at the formula, I know I need the mean. So the mean for X is going to be what? 3, right? And the mean for Y is going to be 6. And I just did that by eyeballing it because I'm thinking balance point of the distribution. These scores are equally distributed around the mean, so I know those are going to be the mean. So if I have my X's 1, 2, 3, 4, 5, and then I kind of follow the direction. This is kind of the way I think of it. I'm going to follow the directions of my formulas. I'm going to say X minus 3 minus 3 minus 3 minus 3 minus 3, right? And that is going to equal what? 1 minus 3 is what? Negative 2, negative 1, 0, 1, and 2. And then I'm going to do my Y scores. So 8, 7, 6, 5, 4. And then follow those directions again. Y minus the mean. Gosh, that's terrible writing. 8 minus 6, 7 minus 6, 6 minus 6, 5 minus 6, 4 minus 6. Okay. Equals. Okay. 8 minus 6 is 2. 7 minus 6 is 1. 0. Negative 1 and negative 2. All right, now it tells me to multiply them and then sum them. All right, so I'm going to say negative 2 times 2 is negative 4. Negative 1 times 1 is negative 1. This is 0. Negative 1 again, and negative 4 again. Now I'm going to sum. So that's negative 4, negative 4, so that's negative 8, 9, 10. Negative 10 divided by, tells me n minus 1, so I have 1, 2, 3, 4, 5, minus 1 is 4. So that's negative 2.5, which if you click back up to the previous slide, you can tell that that is what it's supposed to be. So we did calculate it correctly. Now, what's hard about doing this on a video is I don't have my audience to tell me when I have added or subtracted wrong, because it happens, right? I don't know why writing numbers on a whiteboard or doing math up at the board just kind of makes me paranoid that I'm going to make a mistake. So, but again, that's another class, another lecture. Okay, so -2.5. Now the negative we get, right? Because our scores are traveling in opposite directions. So we have that inverse relationship, or that negative relationship is what sometimes it's called. So the fact that it's negative is great, right? Because we knew we had an inverse relationship going on there. Okay. Now, that's our question. Let me bring it back up here. The kind of downside to covariance is we don't really have a frame of reference. Okay, so we have this -2.5, but it's -2.5. You know what I mean? And we don't have something to say, oh, that's large or that's small, other than 0 means no relationship. But I don't have any idea how strongly negative this is, or how weakly negative. I don't think that's the right way to say that, or how weak this relationship is. I can just say, okay, it's negative, and it's -2.5. All right, so that's a limitation for sure of covariance, and we'll talk about that again in a second. But let's think about this question. It was a question on one of the homeworks, so let's just think about it together in case anyone had a question about that. It says you conduct a study to evaluate the relationship between self-esteem and relationship satisfaction for 10 married women aged 20 to 24. You measure both variables on a continuous scale and discover the covariance between the scores is 5.5. Later, you find another participant and add her scores to the rest of the sample. Now you have 11, and recalculate the covariance. If the additional participant scored at the mean for the self-esteem measure, which of the following will be true of the new covariance? All right, so now I'm going to say, if you want to pause and work this out or think about it, go ahead and pause. So I'm not going to give you pause time because I still don't have that little Jeopardy song ready. Okay, so what I'm going to do is come back over here and really quickly copy this, because I know that, in fact, I'm not going to do that. I'm just going to paste it in. All right, I know that this formula, having it in front of me, is going to help me figure this out. So I'm going to go ahead and pull that formula together. Okay. And we may also click back to our previous slide. So we don't know a whole lot about what's going on here, but we do know that the covariance, it was 5.5. All right. So if I'm thinking about this, let me pull this. Let me pull this over here if it'll let me. Stop inking. All right, I'm going to pull this. Stop. I'm going to pull this down a little bit if it'll let me, because I think that will help. Not having to write a bunch of stuff over. Okay. I'm thinking about this. So I measure both variables, self-esteem and relationship satisfaction. Okay, so I'm just going to call X. I'm just going to write a little self-esteem, and I'll call this relationship satisfaction. All right, and so I had 10 people, so 10 minus 1 is what? 9? Okay. And I came up with a covariance of 5.5. And that's pretty much all the information I have. Okay. But now I've added a participant and recalculate the covariance. If the additional participant scored at the mean for self-esteem, which of the following will be true? All right. So they're not telling me anything about this, right? I don't have any information about this to add. But I do know for this, my new person scored at the mean, right? Isn't that what it said? Additional participant scored at the mean for the self-esteem measure. Yeah, so she scored at the mean for the self-esteem measure. But again, this relationship satisfaction for the new person is a mystery. All right, so I'm going to pull you back to this slide over here. All right, what about this person who scored at the mean here? What did that contribute here? When we subtracted, we got 0, right? Okay, so if I'm thinking about it in this context, the person that scored the mean here is going to end up with a 0, just like our person in the slide above ended up with a 0. So it really doesn't matter what this is, because if I know that she scored a 0 here, whatever, this could be 1,000,000, right, or 1,000. If I say 0 times whatever, I'm still going to get 0. Okay, so when then I go to sum this information, that person's not going to contribute anything up here. My sum is not going to change at all, because I have a 0 for self-esteem times whatever relationship satisfaction is. So she's not going to contribute anything, right, to the numerator. But what's going to happen to our denominator, right? It's not going to be 9 anymore. It's going to be 10. Okay, so numerator stays the same. Now I'm dividing by a bigger number. So what happens to your answer or your quotient when you divide by a bigger number? If I said 10 into whatever the numerator is versus 9 from before, all right? If it helps, think about pizza. If you divide a pizza into more slices, what happens to the slices? They get smaller, right? So the covariance is going to decrease. Okay, so it's going to be C, covariance will decrease. Now that is kind of looking at it mathematically a little bit, looking at the formula. If you think about it kind of conceptually, or contextually, I guess you could think. If covariance is a measure of relationship, and if I want to think of it as, I want to be able to predict one score with another. You know, maybe I want to predict relationship satisfaction with self-esteem. Well, if covariance is a measure of relationship, and she scored at the mean for self-esteem, that's not really going to be very helpful as far as creating some sort of predictive power or explanatory power. It's not really going to help us sort of describe that relationship, because she's just scoring at the mean for self-esteem. So it's not going to help us at all. And because we're adding a person, it's hurting us, right? If we're trying to see a change in our numerator by adding a person, well, she's not helping. And again, she's actually hurting us by being another person, by making our denominator larger. So our measure of relationship actually goes down, because we're doing less of a good job kind of describing that relationship by adding that other person. She was not helpful. Okay, so far so good. There are a few things to consider. Are there maximum or minimum limits on magnitude of covariance? No. And so that's what I was talking about before. It'll be in the context of the data set, but there's not really any way of comparing it to anything. You know, it's either 0, or it's more than 0, or less than 0, but that's about it. When will covariance equal 0? When the sum of the cross products is equal to 0. And so that's up here. You can kind of see that. When the sum of the cross products. Okay, so cross products would be this. So x minus the mean of x times y minus the mean of y. And then you sum. So if this sum had been 0, that's what it's talking about, the sum of the cross products. Because if the numerator is 0, whatever you divide into it is going to be 0, right? If your numerator is 0, even if you had like 100 participants, 99 into 0 is still going to be 0. All right, that's what that point is talking about. Add one score at the mean of the variables, and what happens to the covariance? Well, we just saw that the covariance will decrease. All right, so let's look at a few examples. Again, we have x and y that could stand for any two variables. I think in class we were looking at something like grade level, 1, 2, 3, 4, and reading level. So as you would expect, as the child's grade level increases, their reading level increases. So what we talked about before, these two variables are kind of traveling in the same direction. As x increases, y also increases. Here we have the opposite of that happening. As x increases, y is decreasing. So we have that inverse. Our variables are kind of traveling in opposite directions. As one increases, the other decreases. Maybe this is still grade level, but maybe this is number of trips to the bathroom every day, or during school. Little kids need to go to the restroom more. As they get older, they can manage, or maybe these are like whole class trips to the restroom. You know how when you take the whole group to the restroom, so you have to do it more at the younger grades. As they get older, you get down to just a couple times a day where y'all go together. Okay, so anyway, I got sidetracked. As one variable increases, the other variable decreases. Inverse or negative relationship. And then finally over here we have an example of no relationship. If I'm looking at x, I see 1, 2, 1, 2. So not really increasing or decreasing. And if I know what x is, I don't really have any kind of predictable pattern going on here, any way to sort of imagine or predict or try to explain what's going to happen with y. It's just kind of all over the place, right? And if I take these very small data sets and I graph them, using a scatter plot or scatter graph, you can visually see it. So the stronger the relationship, the more the dots that you create are going to line up into a straight line. So for example, in the positive relationship, we had 1 and 2, 2 and 3, 3 and 4, 4 and 5. And when we plotted those, they made this nice, beautiful line. So the more the plotted values create a straight line, the stronger the relationship you have. Same thing for negative relationships. It's just our line goes the opposite direction. And then these are also plotted according to the data on the other slide. And then visually looking at no relationship, it goes right along with that line idea. There's not really one straight line that's going to capture most of these dots. If the opposite is true about the lines up here, the more of a line they make, the stronger the relationship. The same thing here. The less of a line any of these make, and I'm talking one line, like I could do one line here and one line here, but I'm talking about if I can only draw one line, there is no line that captures that information the best. So we say there's no relationship. Just looking at it visually. All right. And if we go through and we calculate covariance for each of these, we can see what the values come out to be. We have that last example with 0, so we could see visually there's no relationship. Here we have the inverse. X is increasing, y is decreasing, and here we have x increasing and y increasing. So we have positive 1.67, negative 1.67, and 0. But the question is, how do we interpret these? And that's because covariance is in a squared metric and is therefore hard to interpret. So that is exactly the problem we had with variance, in that it gave us an initial kind of idea of how spread out our scores are, but not much else than that. So covariance gives us a little bit of a look into, okay, is it a positive relationship, a negative relationship, or no relationship? But we can't do much beyond that. So, there's another statistic, and it's Pearson R. Pearson R is going to allow us to remove the influence of standard deviation. So we take covariance and we divide it by the standard deviation of X times the standard deviation of Y, and we come out with this Pearson R value. Pearson R, this measure of correlation, is really critical to a lot of statistics we do from here on out. The general linear model that I mentioned in another presentation really depends on Pearson R. And so understanding Pearson R is very important as we progress through this material. The good thing about Pearson R is it does have this nice kind of clean range. The range of Pearson R, it's limited to go from -1 to +1. So it tells us a couple things. It tells us the direction of the relationship, whether it's positive or negative, and it tells us about the strength of the relationship between the two variables. It gives us that important frame of reference. So just some things to remember. If R is on either end of that range of that frame of reference, so if it is a +1, then the relationship is a perfect positive relationship. And then -1 is the opposite. It's a perfectly negative relationship or inverse relationship. And if R is 0, then there's no relationship. Now, if covariance is negative, Pearson R will be negative or positive. Okay, so you can stop and think about that if you want to, because I'm gonna go ahead and tell you the answer to that. And I'm going to show it to you by looking here at the formula again. So it's asking, if covariance is negative, what will Pearson R be, negative or positive? And so for that, I want you to think about standard deviation. What will standard deviation always be, negative or positive, or could it be either? Right? Standard deviation can only be positive, and so if covariance is negative, R will also be negative. And that makes sense, because if covariance is telling us we have a negative relationship, when we're converting it to Pearson R, all we're doing is standardizing the covariance. And so we're not changing it. Remember when we talked about z-scores and we said that we're not changing the scores, we're just putting them in a new metric so that we can compare them across studies? And that's what we're doing here. We're taking the covariance and we're standardizing it, but we're not changing it. So it makes sense that as we just kind of change the metric, if I'm, how tall am I? If I'm, say, 60 inches tall, then how many centimeters would that be? I'd have to figure it out, times 2.54, whatever that is. I'm not changing my height. I'm just saying it's in a different metric. I just measured it in centimeters instead of in inches. I'm 5'6", by the way, so that would be 66 inches, right? Okay, so the answer to that question is Pearson R will be negative. All right, so let's look at this question. For which of the following will R not equal the covariance for variables X and Y? All right, and again, what I'm going to do is reach up here and grab this formula, because I think it will be helpful for us to look at it while we go through this. Okay, so I'm going to move this, how about right here? Okay, so we are going to do just a little bit of trial and error looking at this. So it wants to know, and again, pause it, go through it yourself if you want to. I've kind of given you a hint that you need to use the formula. So I want to know in which case will R not equal the covariance? Okay, so I don't know what R and covariance are, but I know they're supposed to be equal. And you could even like put in a value if you want to, but I'm just going to imagine that if this standard deviation is 1, and this is for A, by the way, and standard deviation for Y is 1, 1 times 1 is 1, right? So 1 into anything is just going to be itself, right? Does that make sense? So in this case, covariance and R are going to be equal, but this question says not equal. Okay, so it's not that one. Now I'm going to try this next one. So 1 and 2, 1 times 2 is 2. Aha! 2 into covariance, it's going to split that covariance in half, isn't it? All right, so maybe this one. I'm going to try the others first. 0.25 times 4. Well, what is 0.25 times 4? That's going to be 1, right? So we're going to be back into this situation that we had the first time. So it's not going to be that one. And then the last one, 2 times 0.5, which again is 1. We're going to have the same situation we had in A and C, in that when we multiply, we'll end up with 1. 1 into whatever is going to be itself, right? So in those cases, covariance and R are going to equal the same thing. But here, because our denominator ends up being 2, whatever covariance is, 2 into the covariance is definitely going to change for R, right? So in this case, they're not going to be the same. So even with the limited amount of information, we were able to figure it out. Just kind of had to think through it. Okay, so let's talk for a second about comparing Pearson R coefficients. In the first situation, maybe you conduct a study and you're looking at the relationship between a couple of variables. Maybe time spent out of school for referrals and what would be something that would decrease. Let's do for the first one, for the first study, situation A, we have an R of negative 0.3. So that could be, sorry, get my pen to work here. This could be number of suspensions and grades. Right, so you can imagine that as the number of suspensions go up, the grades are going to go down, right? As you're suspended more often, the bigger the number of suspensions you have, the lower your grades will be. All right, so you look at District A and then you look at District B. Or we could say District number 1 and District number 2. And you find these two Pearson R's. So in which case is the difference between the R's the biggest? So here we have a difference of what? This R is negative 0.1. And down here, this R is negative 0.1, right? So maybe in situation B, you're looking at only special ed students, students identified as having a learning difference or other type of disability. You find that this relationship is even stronger, right? So as they are suspended more, their grades tank even more. Okay, so the idea here is, or the point to make here is that Pearson R itself is ordinal. And so even though, and we'll talk for a second, in order to calculate a Pearson R, you need two intervally scaled variables. But when you're looking at Pearson R going from the negative 1 to the positive 1, this is actually an ordinal variable. So all we can do is put things in order, because we really can't say that this 0.1 is exactly the same as this negative 0.1, I should say, not 0.1, negative 0.1. Okay, we really can't make that comparison. Now, what we can say is, in both of these situations, the relationship is negative. In this situation, it's a negative 0.3. In this situation, it's a negative 0.2. You know, and similar things for situation B. But that's about it. We're kind of limited. But what we can do is, on the next slide, we can square Pearson R so that we can compare the differences, right? So if I squared the 0.3 and the 0.2, I'm going to get the 9.09 and 0.04. And then if I square the negative 0.9 and the negative 0.8, I'm going to get these values and end up with a bigger difference. All right, so why is that happening? That's so weird. Okay, why does that work like that? And let me see if I can kind of talk you through it and give you a little bit of an understanding of what's happening. If you think about Pearson R, and if 0 is no relationship, and over here we have negative 1, and over here we have positive 1. Okay, as we approach 0, what happens to the strength of the relationship? So what if negative 0.2 is right here? Oops, these are negative, sorry. Negative 0.2 is right here, and then, stop going away. That's like the magic tick mark, isn't it? It's just going away. That's terrible. Okay, but as the values get closer to the negative 1, as in situation B, can you see how the 0.9 and the 0.8, the 0.9 and the 0.8 are closer to the negative 1? And we said this was perfect, right? Perfect negative, or perfectly inverse relationship over here. So these relationships are stronger, right? And so it would be hard to say that this 0.1 difference is the same as this 1 point difference in terms of the differences between Pearson R's. So we know this is a little stronger than this, and this is a little stronger than this, but if we want to make some kind of direct comparison as far as the amount of differences, we need to do something besides just say negative 0.1. All right, now when we square these, what we can do is talk about them in terms of percentages. So this could, if you wanted to talk about it that way, become 9%, and this could become 4%, this 81%, and this is 64%. Whenever we talk in terms of percentages, it becomes what we call an effect size. So R squared is an effect size. It really gives us some sort of practical implication or indication of what's going on here. So if I say I could say, let's go back to our number of days out and grades, because grades are going to go down as number of days suspended goes up. So I hate to try to write all this in the chicken scratch. The number of days absent, and you can imagine that says due to suspensions, can explain or predict 81% of the variability in grades. Okay, if you're like a Venn diagram type person, you might think of it like this. You have your absent information here, and you have your grades here. And so if you're thinking about overlap, they share about 81%. So this is grades. They have this right here, the shared variance is 81%. Or if it makes more sense, the number of days absent can explain or predict 81% of the variability in the grades, right? So what it's giving us is a little more user-friendly, I guess you could say, because if I'm writing or if I'm reading and I see Pearson R as negative 0.9, well, that means something to me because I deal with this stuff. But if I'm, someone who doesn't calculate Pearson R regularly and I really don't know what it means, or I don't remember from my stats class, this kind of a sentence or this kind of a description over here, this is going to be a lot more meaningful. And when we do our null hypothesis significance testing, we're going to talk about the difference between practical significance and statistical significance. So you've probably read in a journal article, oh, the finding was statistically significant, right? So that's your statistical significance, but how useful is that finding? What's the practical implication of it? And that's what effect sizes do for us. And so this R squared, all these R squareds, are your effect size. So in situation A, there is some impact. So 9% of the variability in grades can be explained or predicted by the number of days absent for your general ed student. But when it comes to special education identified students, then the impact is much greater, right? Okay, so I think I have beat that point to death. Let me go on to the next sentence, the next slide. Okay, so this is where just kind of recap. So we can look at Pearson R values to determine the direction and the strength of the relationship. We can compare Pearson R values to determine which of the variable sets had a stronger relationship and in which direction the relationships are, but we can't talk about the magnitude of the differences, right? And that's kind of what I was hoping I said anyway before, in that we can look at and see, okay, this had a stronger relationship than this had a stronger relationship than the 30, and we know they're both negative, but we can't talk about the magnitude of that difference. I can say, yeah, it was stronger, but I can't really talk about the magnitude of that difference until I square to compare. So before you run a Pearson R, what you want to do is check that your variables are intervally scaled or higher, so interval or ratio. And this is kind of what I was trying to get at before. We have to have interval data to calculate a Pearson R, but Pearson R itself is ordinal, all right? And so that's kind of what we were talking about before, in that you can tell the direction and the strength of a relationship, but we can't compare the magnitude of the differences until we square. Okay, so if that totally confused you, the take-home message here is you need two intervally scaled variables. So just to refresh your memory, that means no categories and no ordinal data, right? So you could not calculate Pearson R for gender and reading level, or gender and math scores. You could not do that. No Pearson R for that. But you could do reading scores and math scores, because those are both interval. You could do age and math scores, because those are interval. See what I mean? You have to have two intervally scaled variables. And then once you calculate Pearson R is actually ordinal. So we can't really talk about the magnitude of the differences until we square those Pearson R values. All right, and here's kind of, again, once we square it, it becomes a variance accounted for effect size. And this is kind of a generic sentence of what I was trying to describe above. All right, and in conclusion for now, you have to have continuously scaled variables, which is what I just said. It's the foundation of all classical statistics. And within this general linear model, all most commonly encountered classical statistics are correlational in nature and yield an R-squared type effect size. All right, so we're going to stop there for this, and I will come back with another much briefer look at some issues of correlation.